In this video, I will introduce the exponential function y is equal to e to the power of x. As you should know, this function only takes positive values. The exponential function is the inverse of the ln function. To see that, we can just take the ln and obtain ln y is equal to x. Noting that y is positive, strictly positive to be precise. The exponential function is used in many areas. It will pop up in the case of differential equations, and is also important in the context of continuous time finance. In the second part of this video, we will explore an application in continuous time finance where the exponential function matters. The exponential function has many useful properties which can be easily derived. Now let a and b be parameters which are element of R. The following holds. E to the power of a times e to the power of b is e to the power of a plus b. E to the power of a divided by e to the power of b is e to the power of a minus b. And finally, e to the power of a to the power of b is e to the power of a times b. Another useful application is to rewrite mathematical problems where we use a power function. So for instance, for any positive a, the following relationship holds. So a to the power of x is equal to e to the power of k times x. So a has to be strictly positive. Now this is very often useful to rewrite problems in terms of the exponential function. Now we can easily find the value of k so that this equation holds by taking the ln function on both sides, which obviously gives x ln a and k x. Now we can kick out the x on both sides and we have the relationship we want. Now, as mentioned at the beginning of this video, in continuous time finance, the e function and also the ln function are really useful. Time can be modeled either as a discrete time model or a continuous time model. In discrete time, we basically can count time. So you have 1, 2, 3 and so on. In continuous time, time flows in a continuous manner. Now this is useful in calculations because, for instance, you can differentiate without much of a problem. So as an example, I want to illustrate continuous compounding. So basically getting an interest payment instantaneously in every split second. So let me imagine putting some money away and we only get one single interest payment. We could, for instance, describe this interest rate as a rate L. So in our case, at the end of this 1 year, we would obtain 1 plus L. And L is a small positive number. Now, if we get a payment every 6 months, we could also find a rate R so that the following equation holds. 1 plus R half to the power of 2. Now this is a notation which is common in finance. It's kind of an equivalent rate. So I take an interest rate R, I divide by 2 because I have 2 interest payments. Now power of 2 obviously applies because in the first 6 months I get the interest payment R half, and then it's again applied for the second 6 months period. So if we multiply this out, we obtain obviously the following is equal to 1 plus R to the power of 2 divided by 4. And it's easy to see that in this case, R has to be less than L because of this term here, which is the compounding effect. So this is the interest on interest effect. Now you can ask yourself what happens if I have not 2 interest payments, but maybe 3, 4, 5, or 10 or n payments. So we can generalize that. So generalizing to n payments, we obtain the following. 1 plus r divided by n to the power of n is equal to 1 plus l. On the left-hand side, we actually have a polynomial of order n. So if you want to explore the relationship between r and l, we have to deal with a polynomial of order n. So finding the roots of this polynomial is computationally not necessarily very straightforward, in particular when we look at very large n. So now we are interested what happens if n becomes very large, or in the limit n tends to infinity. Now first of all, we note that in this case r divided by n tends to 0 plus. So we go to a very, very small, slightly positive value. Now we can simplify the equation by taking the ln on both sides, using the rules we learned in the previous video. So that gives n ln 1 plus r divided by n is equal to ln 1 plus l. And we will get back to this equation in a few minutes. So now what I want to do is I want to use an approximation, because I argue that the left-hand side can be simplified if we look at the case where r divided by n becomes very, very, very small. To visualize the approximation, let's have a look at the ln function. So we know that the ln function takes the value 0 if x is equal to 1. So we know the value at this point here. We also know the slope of a function. So if we take the first derivative, so d dx ln x, obviously it's 1 divided by x. So if we evaluate this first derivative at x equal to 1, the slope at this point is equal to 1. So if we start at ln 1 and a tiny bit, we know that the value at the start is basically 0. And now if we move a tiny bit to the right, the increase in the value of the function is covered by the slope, which is equal to 1 times the change. So put differently, moving a tiny bit this side by r divided by n, we know that the value we gain is basically r divided by n. So that's a linear approximation. Later in this course, we will make this more robust. We will generalize this when we talk about the so-called Taylor expansion or Taylor series. So getting back to our equation, we now argued that this part here is approximately r divided by n. And this obviously simplifies our problem. So now we can write n times r divided by n is the ln 1 plus l. If we simplify this further, obviously we obtain the following. And now we can apply the exponential function exp on both sides. If we do this, we get e to the power of r is equal to 1 plus l. Again, it's the inverse of the ln function. So here you have it. Now we have this relationship between our annual payments of rate L and our continuous rate R. I see you in the next one.